Okay, welcome back. Today our lesson is dividing complex numbers. Now, when we learned adding, subtracting, multiplying, they all kind of felt natural, I guess, if you remembered that you could treat I like a variable and then simplified it accordingly. But dividing is undoing multiplication, and if you remember that multiplication was a little bit complicated, especially with that I squared becoming -1, how on earth could we divide? Well, we're going to tackle that question today. First, we're going to use mistakes are important for our mindset message. This is easy to make little mistakes on, so I just want us to remember, don't get deflated about that. Just push on and you can do it. Main goals today. We're going to learn a new vocab word. It's okay that you don't know it right now. Understanding the conjugate of a complex number, and then dividing two complex numbers. Prior knowledge would be what we learned about adding, subtracting, and multiplying complex numbers. And then actually, there's one little thing that's going to bring back systems of equations, specifically linear equations, and those substitution and elimination methods. Don't worry about those if you don't quite remember. We will actually review, especially the elimination method actually is the main one that's going to be helpful today. So we're immediately going to dive right in. Let's say the product of a number z and 4 minus I results in 14 plus 5i. Right? So z is a complex number. And we want to figure out what is z. Well, do you realize how we're just thinking backwards with multiplication? So really this is actually asking about division, technically. But it helps to phrase it in this way. Let's take a look at just putting down what we know. Sometimes in math you have to just go for it and see what happens. So what's been given is that some number times this equals this. Well, again, we know that probably has to also be a complex number. So it's probably better to actually put it into the form of a complex number. But the thing is, we don't know what those a and b values are. We're trying to figure that out, right? So we do know 4 minus I times that gives me 14 plus 5i. Now what to do? Well, you probably can guess that the only real thing that it seems to do would be, let's multiply this out and see what happens. So I've done all this out, and you could pause if you need to just double check each little step here. Don't forget I squared is -1, so it always changes that sign. In this case, it's just going to change this to a plus b, and then work it out. But in the end, what we get here is this portion without the I, and then this portion that's attached to an I, must line up with the outcome, right? 14 must be 4a plus b, and 5 must be the same as -a plus 4b. So what we've got here is a system of two equations. Now, if you recall, elimination works in such a way that if you line these up, if you were to add or subtract the two equations, basically you're combining them into a new equation that works together, basically, as the combination of the two. But the goal is to eliminate a variable. You'll notice whether I add or subtract, the a or the b won't be eliminated. We kind of have to prepare for it. So let's remember what to do here. Remember that we can scale an entire equation by a single number, and it results in an equivalent equation. So for this one, if you notice, I'm going to multiply everything through there by 4, and it's going to result in -4a plus 16b equals 20. Why did I do this? Well, because now I can add these two equations to each other, and you'll notice that the a terms will be eliminated. So b plus 16b gives me 17b, and 14 plus 20 is 34, and we can therefore see that the b value we want is 2. And now that we know b, we can use either of our original equations. Let's just use the top one and replace b with 2. If we solve that, we get a equals 3, and so the complex number that I was seeking is 3 plus 2i. Now you might be wondering, man, this was a little complicated. Is there a better way? Well, actually, it turns out the answer is yes. However, it's really good practice right now to get practice with solving systems of equations and to realize this process of just trying what you can. So I want you to do a similar problem as we did last time using that method right now, and then we'll check our work and we'll explore this further. So you should get 8.2 plus 4.6i. If you didn't get that, you can go ahead and look through this. Otherwise, you can just skip ahead to the next portion of the video. So again, here's the setup, same as we did before. Just be careful with each step and check that, and then you should end up with this system of equations. And following a very similar set of steps, once I have these two equations, We scaled by 2 here. Now you could have done different things. You could have maybe multiplied this one by 2 and then eliminated the b's by subtracting the equations. So there's different ways you could go about it. But in the end, you should still get b is 4.6 and a is 8.2. Now let's prepare the way a little bit for our simpler method of doing division. But we have to lay some groundwork first. First, a vocabulary word. There is a special type of number in relation to any complex number that is called its conjugate. And that's different. We never thought about that with real numbers because essentially real numbers, basically they just only had an opposite. So for example, 3's opposite is negative 3. Now, there's a difference between conjugate and opposite. Conjugate only changes the sign of the b number, but it has very important special properties. So let's say we have a complex number z, 2 plus 7i. Go ahead and find the sum of z and its conjugate and the product of z and its conjugate. Remember, this bar on top means the conjugate, right? So if z is 2 plus 7i, z bar is 2 minus 7i. Notice I did not make the 2 negative, only the 7. Checking your work real quick, something important happens with conjugates when we add or multiply them. Notice here when we add them, since those parts are opposite, they cancel out. So we really are just ending up with a plus a, in this case 4. And same here, when we multiply it all out, the two middle terms end up the same but opposite, so they cancel out. And we're left with 4 minus 49i squared, but that i squared changes to plus, and so we get 53. Now this was not a special number I chose. In fact, this canceling business, because it's a conjugate, would happen no matter what complex number I chose. So this leads us to a suspicion here, and it turns out it's not hard to prove that z and its conjugate, if you sum them or if you take their sum or their product, it is always going to be a real number. Let's set this up and do this. So we'll just call z a plus bi like usual, but its conjugate is simply a minus bi. So if we go ahead and take the sum and the product, simplify it out, go ahead and finish that yourself and see that it really is just going to be a real number. And furthermore, we're going to have a formula for it. Here's what you should have gotten. When we cancel these things out, you're just left with twice the value of a. So the sum of two complex conjugates is always going to be 2a. And then the product, again, you'll see these middle terms cancel out, and the I squared is negative 1. So it turns out that when we have the product of two complex conjugates, it's always going to be the sum of a squared and b squared. Which is funny, because you've probably learned in the past that there wasn't a way to factor the sum of two squares. We've learned that you can factor the difference of two perfect squares, but not the sum. Well, if we allow for complex numbers, then it turns out we can factor the sum of two. All right, it's time for another example. Now you might say, wait a minute, didn't we already do this one? Well, we did. But a complex numbers conjugate that we just learned about can actually be a very helpful tool to tackle this in a little bit simpler of a way. So if we set this up like before, but instead of doing what we did before, actually realize that this product relationship can be restated as a division relationship, it turns out there's something really helpful with the conjugate, like I said, that we can use here. Now, you probably agree, multiplying anything by 1 does not change the value of that original thing, but 1 can show its face in many ways, right? Anything over itself is equal to 1. So the cool thing is, we can choose whatever we want in the top and bottom as long as it's the same thing. And we'll explain why this ends up working soon, but watch me here. I'm going to take the conjugate of the bottom and I'm going to multiply it down here, but if I do that, I must also multiply it up there. And the reason why that's helpful here is because we already said if you multiply a number and its conjugate, it always is a real number. There's no more I anymore. So I multiplied the top out and the bottom out. And remember, I took the shortcut for the bottom based on our formula, right? If you have two conjugates multiplied, then it's always going to be the result is a squared plus b squared. So our a is 4 and our b is just 1 in front of that I, right? Okay? And don't forget, I squared makes this change its sign because it's -1, so it becomes a -5. 56 minus 5 is 51. So in the end here, I get 51 plus 34i over 17. So again, why was that conjugate helpful? Remember, it always makes a real number. So in the end, this thing, we can divide those separately, and you'll notice 51 over 17 is 3, and 34 over 17 is 2. So this ends up being 3 plus 2i, and it turns out that actually we can divide two complex numbers to get yet another complex number as well. Okay, so to wrap things up today, let's just give you a little bit more practice. Divide the following pairs of complex numbers, and again, you can use that conjugate method that we just talked about. One thing to mention that sometimes students try to do is, sometimes students just want to treat these numbers separately, so 5 over 4, and then 10i over 3i, and separate the two fractions. Remember, we cannot separate addition in the bottom of a fraction, if you think back to what we learned about fractions, so we have to take care of it in the way that we've been learning. So why don't you go ahead and do these, and then we'll check the work and be done. So here's the final work and answers. You can go ahead and just check the final answers. If you got them right, then you're good to go. See you later. If not, just double check the work here and see what happened. Reminders here. Remember, every time you see an I squared, that always changes the sign. So it becomes plus 30, right? So 20 plus 30 is what made this 50, for example. And then now that this is one single thing, then we can split it and divide this by this and this by this to get 2 over and 1 here with the I. And again, just check the other ones. One other quick thing to mention here is, since this is just plain old I, you may have thought that just multiplying another I, doesn't have to be the conjugate technically in this case with the negative I, would just result in a real number as well, but it would be -1. So you could, if you wanted to, have done that, and it would still in the end have resulted in what we got in the end. But if we keep it to this, the nice thing is we're dividing by +1 down here, and so we just get the top as our result, and then we write it as that. So that'll be it for this lesson. So again, happy math, and we'll see you next lesson.